this month is very critical, I think so. Whatever the virus, if we intake actually, virus is not good for us. They are in, okay, they have some side effect. So that's why we prevent and keep confined in home. That is better for few days, few weeks, not days. Okay, so we'll start the UV. Did you go through the UV, any books reference for the spectroscopy?
Ma'am, I read some books, but I didn't get to the spectroscopy part of it.
No, Pavlia, don't you have Pavlia? Yes.
Yes, ma'am, I read from that. I just finished chapter 1. So,
Okay. So I will, if you want, anybody want PDF, so just give an email. So I will send the actually reply with the PDF. Okay. So you can go through these books for study. Okay. So now the next part. First start the recording. It's actually very interesting UV spectroscopy. Initially, the terminologies are something maybe is not. It definitely should know, but after that, when you the analysis the molecule, you can see that is very interesting actually, like a challenge to solve the problem. Okay. So, now still we are not in the starting, just beginning part. Okay. So I start the from the last slide from the previous class. This is the slide actually. So slide UV spectrum, and you can say this is UV visible spectrum. So because I show the wavelength length is 100 to 800. So it includes the UV region including visible, and that is actually modern trend to scan the molecule within this wavelength, lambda in nanometer. And UV spectrum, UV visible spectrum in x-axis is wavelength in nanometer, lambda in nanometer, and the intensity of absorbance in the y-axis. And it looks like that is some model actually, it looks like this way. And it's the maximum peak absorbance, that is the lambda max, is you can identify it in this way. This is the lambda max. Whatever the absorbance they are lower, so maximum intensity for the absorbance is known as the lambda max. This is some model. Now we will go symmetric electronic energy level. That is very important because all UV visible spectroscopy related to the electron transition. Then which level to which level they will transit, that we should know. And we also mentioned already this is involved pi electron only. So what is the distribution? What is the nature of pi level? We can go through some schematic diagram. So that is the actually schematic diagram and their energy level, lower to higher. So sigma bonding level, sigma bonding electrons that not actually all the time involved for the transition. Okay. Some cases it happens, but very rare. Because if sigma bonding breaks, that means molecule does not exist actually. After that, pi bonding is labile, so they can sit anywhere. Where they can sit? They can shift non-bonding electron pair always filled actually by two non-bonding electrons. After above actually this level, up to this level is a room temperature level, and molecule is actually stable with its sigma bond, pi bond, and non-bonding electron. Okay, but after that, I am showing here to another level, energy level, in higher energy level, pi star and sigma star. And I mention here anti-bonding. And it's the distance. You can see the non-bonding is the room temperature level, and the energy gap between the n from this pi bonding level, and N from the pi antibonding level is equal, and it's same for N sigma bonding and N to sigma star antibonding. Then, do you have any idea about the antibonding level? Antibonding, this concept? Do you have any idea? Bonding?
It is formed by destructive interference of molecular orbitals.
Yes, that is. And which situation is arises? Just some qualitative idea.
Energy level increases.
Ma'am, it has more energy and less stable.
No, actually during the electrons in, suppose you have some hydrogen, I'm bonding actually, two hydrogen elements are coming for the H2, formation of H2, so there will be some situation bonding, but hydrogen both have one atom, both have one electron. So when these two electrons are side by side, then what happens? They are not binding, they are repulsive, interference that he mentioned. So they are not in a bonding properly. Their orbital not overlap actually. But when they are far apart from opposite sides, still there is a cloud actually. Okay, there is always a cloud. It's not a single point actually. It's a cloud, electron cloud. So in this way, they can bonding actually, that situation. So when this negative charge are far apart, and there will be some, their bonding happen. But one the point actually, the cloud points are close to each other, then they repel each other. Okay, the situation is close to each other and 180 degrees or apart from each other. Just think about the two spheres for sp orbital. Think, imagine. This is some imagination. So in this point actually, antibonding arises. The concept antibonding arises, and you can, if you go through the theoretical, you can see this some interference of orbitals are happening. So statistically, we can say for suppose hydrogen molecule during formation, there is a 50% chance for bonding and 50% chances for the antibonding situation. Do you understand this thing? Okay, that's why 50%. So 50% is same below the level bonding. So they forms a different type of hybrid orbital and they stable. That's why it is bonding in a lower energy level to make it stable actually. And when the situation is not like that, they forms a empty higher orbital level. And that is if the all sigma bond electrons are go to the sigma star, that means there is no molecule. Okay, there is no molecule. So sigma to sigma star, whatever the is actually possible because the symmetry allow transition, but if it happens, no molecule is there. Sigma, if the bonding is not there, basic bonding, that is sigma, so molecule does not exist. That's why, and it is actually beyond, I can see the comments actually, okay. So later on maybe I will skip. So after that, and another point, sigma to sigma star, the energy actually, what happened? This is actually the dissociation energy, equal to their dissociation energy. And that is reflection in the wavelength not included in the lambda UV visible length, that is 100 within 800 nanometers. Okay, so that part we not consider. So much energy is consumed for the transition so that the molecule will destroy. That is not our actually desire. Now the next part, pi. Pi bonding is the same situation. If the two electrons are in a formation of the hybrid pi bonding, then immediate hybridization according to the concept, they form the pi bonding. And there is a opposite action always there because of the repulsion. And obviously, this energy is 180 degrees if you think, or 50%. Statistically, you can say bonding is 50% and 2 electron are if repulsion, 50% chances for non-bonding. Not non-bonding, they are not in bonding position. That actually mentioned as excited bonding level or anti-bonding level. Okay, so each transition sigma, pi, and these two have antibonding and pi bonding, pi antibonding and sigma antibonding. But for non-bonding, there is no such, because it is the particular one atom are reside. Suppose you have only oxygen molecule, they have such property, not the carbon or etc. So there is no bonding and anti-bonding. They place very suitably, comfortably with a particular hybrid orbital. Okay, but they can move because they are not involved in their bonding purpose totally. They can control the shape and they can control this transition also for their spectral property or their color intensity. So in non-bonding pair, single electron or double electron can shifted pi star or sigma star. Both are possible. So transition from the lower level, not this level, sigma to sigma star not allowed because of the dissociation. Otherwise, all are possible. Pi to pi star, n to pi star, n to sigma star, and pi to sigma star. All are possible for the UV visible spectra, depending on the nature and structure of the molecule. So probable transition, these are actually inhibited, I already mentioned. Otherwise, n to pi star, n to sigma star, and this all are possible. And here is also, I show here only one pi system, pi electron system. For conjugated systems, there is a lots of pi bonding, so lots of pi star are available. So more transitions or more way of transition is possible. And which one is the lowest? That is his most best actually lower energy gap. That is the higher wavelength lambda max for this molecule. This part we will see. Okay, with some examples. Okay, have you any question with antibonding or antibonding? Otherwise, we can go to next one. I just qualitative idea. I am not go into the theory. Theory is very complicated to understand. And for as an organic chemist, it's difficult. We can predict so many things without theory. After the theory will build up according to the result. Okay. Now that is with some example. I again, so one by one molecule. So for sigma bond, we have only transition, so it will destroy. This will happen actually. For this one, what happens? There is a C double bond C. When one sigma bond, one pi bond. So we have sigma and there is a pi bond. So sigma we already mentioned. So this way, these are actually allowed. Okay, this pi transition is allowed, and it's reflection a one transition peak for this moiety. And then C double bond O. So there is also another pi electron involved, that is non-bonding. Now what happens? There is a three-way we can see the transition: n sigma star, n pi star, and pi pi star. Okay, so but you can say that pi to n, because n is filled up. So that's why that is not possible, and also the minimum energy it go up the room temperature level. So that's why n sigma star, n pi star, and pi pi star is the possible way of transition for this C double bond O, that is keto type of compound. Okay, and also you can see the all transition, which one is the lower energy gap, that is actually the lambda max. So which one here? This n to pi star is the lower.
N to pi star.
Yes, so that is actually corresponding to the, because that is very frequently done. Okay, so this probability is maximum. So that's the lambda max for this molecule. Okay, you can guess like this way. Sometimes not possible all the time, but if the molecule is very simple, so you can guess. Now the conjugated system here. So here is something different. Obviously, is a butadiene system. Once the butadiene system, and we have one sigma, no problem. Is no transition, don't think. But the pi and pi 1, there is a two conjugated. So pi 1 I show here on the line pi and pi, and then I split again pi 1 and pi 2. That is actually happened because they are in a conjugation. Okay, so always after mixing they will give it to different level pi 1 and pi 2. Energy level are splitted. Not so much actually. I am for simplicity showing their gaps so big, but it's a very narrow actually. Different pi 1 and pi 2 energy gaps is very narrow. Okay. For simplicity, I want to show you like this. They are splitting because of the conjugation property and some hybrid nature. Okay. So one will always in this case we got a one energy level lower and one energy level higher by hybrid mixing. Okay, and this will give a two splitting. And same thing happen for the pi star level 2. Okay, same thing happen for the pi star level 2 also. Okay, we only consider it as pi, so that's why I am showing here this way. So pi 3 star and pi 4 star. So how many electrons are filled up in the lower energy level? Pi 1 and pi 2, and higher energy level pi 3 and pi 4 star. Then probable transition. So this is the minimum energy gap, pi 2 to pi 3. Okay, so that is the most probable and most frequently, and that is actually lambda max for the molecule. Others are all possible. Others all are possible. Okay, so pi 2 to pi 3 star I am showing for the minimum energy gap and lambda corresponding lambda max. But all pi 1, others are possible pi 1 to pi 3, pi 1 to pi 4, and pi 2 to pi 4 2. Okay, all are possible here. So there is a different type of, because of more pi electrons is pi system, we will get more possibility. But which one is the more energy gap is less, that is the maximum characteristic for particular molecule, and that depends on their structural property. Okay, so if because of their environment, pi electron environment, each molecule has particular absorption for a particular compound, specific. That we compare actually, that we study in UV visible spectra for their analysis, structural analysis. Okay, this slide is clear. So you can go, you can move. Tell me. You can move.
Yes, sir.
Okay, so this part now, if you go through the Pavia, this is a very popular actually picture for understand this conjugation system and how the transition are slightly slitted with the conjugation. You can go through in the sentence part for explanation. You will get the good idea. Now the text part. Now what happened? Lambda max for CH2 is 171. Okay, because and then lambda max for CH2 double bond CH2 5 is 177. Why this difference? Lambda max is higher means energy gap is lower. Then tell me why this will happen. Pi electrons are same. Then what happened in this two simple molecule? The system is simple single pi electron system, but still showing two different lambda max. Why this happened? What is the difference? What is the difference? Very simple. Tell me.
More number
Plaza
of
effect
sigma bonds.
increases the cloud density of electrons.
Can't hear actually properly.
Conjugation.
Huh?
Plaza effect increases the
Yes,
cloud
yes,
density.
plus I effect is true because plus I is pushing the electrons, so the transition probability will increase. Is clear? All effects we already mentioned previous classes starting actually, and you know that's involved now. Conjugation, inductive effect, etc. So there is a inductive plus I effect, and that's why these pi electrons are more, electron availability is more, okay, but tendency to transition is more, okay. With mild energy they will shift it, everything. So that's why there is a reflection for the lambda max, the nature, and that is a model with respect to this one. Now next this one is lambda max 184. Now what happened?
Ma'am, two more effects of
Side
Plaza
plus
effect on a
effect.
conjugated system.
So you can understand that there is a 1 and there is a 2 plus I effect again. So their probability will increase, okay, energy gap is lower and showing the lambda max in higher. Clear? Now this one, 182. Why? These are same, but cyclic system open. Then what happened?
Ma'am, due to ring strength.
Yes, due to ring strength or rigidity of the structure, there will be some energies, not so much, but if little is understand the nature, compound nature is different. So this, so that if you have sample, you can compare with the lambda max. If you have sample, if you have two same type of molecular mass, there you have 6 molecules, carbon actually elements, then you can just run the UV, you can understand which one is which one. Okay, so structure features are, you can actually analysis can be analyzed by UV spectral analysis. This is very minutely, if you very expert in this lambda max calculations and lambda max concept, you will get benefited with its chemical characterization. Now this one. So the model lambda max is a 171 first ethylene moiety. Then what happened with the 130 is so much higher, lambda max is 217 nanometer. What happened?
Due to resonance.
Conjugation. Due to the resonance or conjugation they have, and so that they have some lower energy gap. I already mentioned in this slide actually, lower energy gap, because pi 1 pi 2 is splitting to form the some higher pi 2. From the lower pi 3 star, our energy gap is minimum with respect to the ethylene, and so that its reflection where we show the lambda max value, and it's 270. So with increase the conjugation, the lambda max will increase. That is some shortcut if there is no other restrictions or something. Okay. Now this one, see the reflection. To increase the conjugation, increase the lambda max. So energy is lower, okay, is not proportional. Now this is acetone. Lambda max is equal to 187. Different. Now this one 119. Why? Because this one is a conjugation with the carbonyl group. Okay, so conjugation is very much actually influence the lambda value of lambda max for a particular, and it varies with compound to compound nature or their structure, the functional group. Now, so each cases in this is actually red shift happen, increasing conjugation. Clear? Red shift example. There is a lots of example in books and in Google, so you can go through. to understand the nature of how it lambda mass is actually gives the different value for different compounds. Now this is there is a for acetone. Okay, so pi star is a 150 nanometer, n sigma star is a 190 nanometer, and n pi star is a 272 300 nanometer. Okay. Then just for sometimes we are some questionnaire purposes we are showing this slide. Pi star is a 187 here. Now tell me why this one happened 185, 150 to 185.
Ma'am, plus I effect of
Yes.
group.
Then n pi star 277, same thing. Now for this one pi star is a 219 and n pi star is a 324. So plus I effects and conjugation both plays very significantly the change of lambda max value for this compound, and we thoroughly actually identified this one with this slide actually. Okay, so that is actually something we can gather from this UV visible spectroscopy analysis part. Now go to the application part. That is the principle I mentioned actually. Now, we need some rules to understand for calculation purpose. So, reflect this with calculation of lambda max. So, Woodward and Pfizer actually propose. This is actually so much actually this is assumption initially, but their repeated results are good consistent with the observations, and results are consistent actually with different moieties. So it now becomes rules. And this is actually very minute difference with the theoretical calculations and the experimental values, plus minus 2 actually. So that's why this is some straight-cut way to understand the chemical structure using the Woodward-Pfizer rules. And where this rule applies for diene system and triene system. And these are actually for some natural product, okay, terpene, etc. have this type of moiety, diene, triene, etc. So this natural products are very, actually, the terpenes are very volatile. So if you go to NMR is okay, you can collect the NMR data, and if you run the sample with the particular UV inactive solvent, you will get a complete idea of the structure, what compound you have. Now almost we have a database of terpenes, so no problem. From database by checking and the run of your sample, you can understand which terpene you have in your sample. Okay, what is terpene? Where can get it? Terpene, in one word, what do you say?
Ma'am, it's collected from 5 carbon compound isoprene.
Yes, but is a volatile essential type of oils actually, okay? It's very volatile. Some perfumes are formed with this terpene, sometimes pesticides, some volatile pesticides are using this terpene. Suppose you have neem oil or etc. It's rich in terpene type of moiety. Okay. Now diene and triene system. Simple system we will discuss. Now first point, how much lambda max we decide as a base value for a moiety. So we need some basic moiety. After that we can add. Suppose we have one diene moiety is the base moiety. After that again you have another conjugation. So that is some additive part. So diene is the basic moiety. With respect to this diene, we have different type of moiety. Now first one we'll clarify later on. First we read this one first. Acyclic and heteroannular dienes. Acyclic and heteroannular diene base value is 2 14, base value. Homoannular dyne 253. Okay. Addition, after that, this is the base value. After that, we have to add with the 214 or with the 253 according to the base moiety. So addition of each alkyl group, that is, we already seen the plus I effect is there. And another part, we can go through the ring residue. This will give you have to add plus 5 for each alkyl group addition. If there is a alkoxy group, you have to add plus 6. For halide, plus 5. For pi-pi, each pi-pi conjugation, you have to add plus 30. And exocyclic double bond, you have to add plus 5. So many new terms are there, isn't it? So many new terms. Heteroannular dyne, homoannular dyne, ring residue, then exocyclic double bond. So first we clarify these things, then we'll go for the analysis part. This is dyne backbone, first one. Okay. Then this one I am showing here by yellow. Actually, this is known as endocyclic double bond, and we are familiar with this thing. It is okay. We don't think that is endo. If the two carbon actually form the bond within the ring pi bond, same ring involve two carbon from the same ring form the bond, that is known as endocyclic. Okay, and what is the difference from the exocyclic? Exocyclic, only one carbon from the ring system is involved and other carbon from the outside, not the part of ring. That is exocyclic double bond. Clear what is endo and what is exo?
Yes, ma'am.
Okay, picture. You can remember the picture actually. That's why I am doing this. So this one. So this is the backbone. Dyne system. Acyclic dyne system, this one acyclic dyne system. Okay, and now these two methyl introduced, then what will happen? See, is it clear? Why I am lighting this one, or I can go back to the previous slide. If you want, I can go back. There is a mention for each addition of methyl group, alkyl group, you have to add plus 5. So, for acyclic and heteroannular dyne, we have the base value is 214 for calculation of the lambda max, and then 2 into 5 equal to 2248 lambda max value. So whatever you can actually, by observing the molecule, by drawing the molecule, you can guess the value. Then you run the sample UV. If it's matched, then you can think your structure is okay. If not, you can rethink the structure, pi bond conjugation or etc. Okay. So this is actually more reliable rule to understand the molecule. Tell me. Anybody want to say something?
No, I was just asking if the 214 is from the conjugation in the molecule.
No, base value, only the base value. After that, one hydrogen is substituted by methyl, na?
Okay.
Okay, so actually the dyne I showing here 217, but Woodward Pfizer proposed it 214 for their rule. Usually it is actually 217 actually happens, but they make a observation of the large number of molecules and give a idea that you take the base value is 240 for the butadiene system. Okay. That is according to rule. If you write down here the 217, maybe I will not cut the mark. Okay, but according to Woodward rule, it's okay. Just one, okay? No, it's classic. Okay. Now this is some again acyclic system. Okay, this is not a cyclic moiety. So its value, base value is how much? 214. Okay. Now after that, whole are what? Some alkyl residue. Then its value is 214 plus 1 into 5 equal to 290. You can take this pi bond for the part of this butadiene system because it's apart from the conjugation. Here,
Yes, ma'am.
Okay, so there is no direct actual relation with the pi system, diene system with this pi bond. That's why it's just a part of alkyl group, nothing else. We not consider this pi bond for a conjugation system. Now this one, I go to the next terminology, homoannular diene, and then this one I will go. Okay, homoannular diene. First, homoannular diene, what happened? If the two pi bonds are in the same ring in a conjugation, that is, up to this is a trans system, here it is a cis-butene system within a ring. This is homoannular diene. Clear to you?
Yes, ma'am.
It is make it clear that homoannular dienes having the cis-butene moiety. Butene moiety, not butene itself. Cyclic system having the cis pi bonds are in conjugation in a cis position. That is homoannular diene. Just a minute. আরে বল ওটা তো খুঁজে কোনটা বলছিস খুঁজে পাচ্ছি না তো আর তুই এলে আমি বলে দিচ্ছি আরে আমি তো কালকে পাঠিয়ে দিয়েছিলাম আগেই তারপরে আর কিছু আসেনি আচ্ছা আমি ক্লাস নিচ্ছি হ্যাঁ ক্লাস নেওয়ার পরে তুই আয় মিটিং এর ইয়েটা ঠিক আছে হ্যাঁ আচ্ছা then what happened now there is a red and blue mark okay so what is the meaning of blue mark what do you think and what is the difference from the red and blue mark what is the difference
Blue is
Blue
for
mark is out of
alkyl group.
conjugation with the ring.
yes actually red marks are added because they are part of ring that is known as actually ring residue so this system having two ring residues part but this one is simple alkyl group but their contribution is same but nature is different but here is the same so 253 is the base value for homoannular diene and 3 into 5 one for alkyl group another 2 for ring residue I'm showing just the same value that's why 268 okay now this one this is heteroannular diene here actually heteroannular diene the system will be trans maybe within a cycle or outside that is different okay so there is a lots of way we will go with example here is a simple one cyclic system and here you can see this is cis system here is a trans system that should be there maybe this part also in a ring but trans butane system is there is a heteroannular diene now what is the value will be is the 214 is the base value acyclic and heteroannular diene the base value is 214 after that red 2 are ring residue okay so 214 plus 2 into 5 for ring residue plus 5 I mentioned here exocyclic double bond so this one is also exocyclic double bond so make it sum we will get 229 clear you have to understand with the structure and the parameter by observing and by making your thinking it's clear all things so this slide predict the how to select the base value for diene system acyclic for homoannular system for heteroannular system what is exocyclic double bond and what is ring residue all are in this slide make it clear then we will go further
Ma'am, about I have a question about homoannular diene. Ma'am, from why the 253?
You can understand, one is trans and one is C. Then what happens?
Ma'am, 3 into 5 from alkyl group and from মানে for what is 253?
253 is the base value for cis butene. This is actually trans butene and this is cis butene.
Okay, ma'am.
So there is some lambda max higher, that means lower energy gas. So this system actually makes the lower energy gas. System is different, so that's why the value is 250. There is some orbital actually overlapping, etc. Okay, so that's why.
Okay, ma'am.
Now calculation for this. Now what is this system? Heteroannular dyne or homoannular dyne?
Hetero.
Ma'am, hetero.
Hetero. But both are ring system now. Heteroannular dyne. Now this green, blue one is the
Alkyl group.
alkyl group and red three are ring residue.
Alkyl group.
No, not
Ring
alkyl.
residue.
Ring residue.
Ring residue.
Differentiate the ring residue and alkyl group. Okay. And we consider only the ring residue along with our system, dyne system. Okay, along with our dyne system. Not this beyond this one. Whatever the dyne system ends, then we calculate everything. Not go to the there. Okay, extended part. We only think about the dyne system stuff here. Now we checking the surroundings. What are their substitutions? And here is the yellow part is the one exocyclic double bond. Okay, so base value is 214. Then 3 ring residue, 1 5 alkyl group, and 5 exocyclic. Sum is 239 nanometer. Okay. Clear?
Yes, ma'am.
Some actually exam, this part, some definitions and calculations. So very carefully we will go through, read through, otherwise sometimes we will make a wrong summation, that is not we will consider, but put the value in this way, that we will consider. So provide this data clearly. Summation maybe in very first you will make a 330 maybe, 230 maybe, that is okay. But here this part is very necessary for your answering. You have to identify the contribution from each part actually. Now this one. What is this one? This value, you consider it homoannular dyne or heteroannular dyne? Tell me.
Ma'am, I can consider hetero, right?
Which have lambda max higher. We always take the higher lambda max, no? So here one is 214 and one is 253. Why we consider the lower one? We always take the higher one. So that's why we consider the homoannular is the base point, 253. And then tell me how much it will, how many ring residue it has,
And 3.
and then alkyl group,
1.
conjugation,
1.
exocyclic,
1.
okay. So now see this one conjugation, and 3 blue is alkyl, yellow is exocyclic, and this is extended conjugation. So what is the value now? 253 base value, 3 into 5 ring residue, 5 alkyl group, plus 5 exocyclic double bond, plus 30 conjugation from this conjugation. For each conjugation we have to add plus 30. So that is equal to 308 nanometer. Clear?
Okay, ma'am.
Yes.
I think it's interesting. You will go through the books actually. and you will get lots of example. Now your turn to practice it, understand it, make it thoughts are clear. So there is another rule too. Next day maybe we will go and some questionnaire. This is some solvent polarity we will discuss later on. Up to this we have time. Sorry, I was not able to take yesterday's class. I have planning, but some sudden discussion for the institute closing or not, just for we come or not. Because of this discussion, I don't inform you actually. Next week maybe I will take, because we have shut down our institute for the 1 week maybe. So weekly I will take the classes from home. Okay, so up to this, okay, any book, any Google search, you can get this one. Do the exercise with moiety, this calculation, lambda max calculations, and be confident about this one. So I have not concerned about the summation, exact value, but I am always concerned, see, your identification of the addition is okay or not. That will give you the mark. Okay.
Ma'am, please share the video to the email.
Yes, I mentioned now, your seer will give you the reminder. I will send this video and the Pavia book too, PDF.
Okay, ma'am.
So that you can go through the example also other than this. And you can consult any other source, you can consult, because this is something interesting you will be enjoying maybe initially. Okay, so now, so next we will go for the solvent, and would again another rule, this is for unsaturated aldehyde and ketone, non-bonding part. So diene system have no non-bonding part. So Woodward Pfizer rules, another rule for unsaturated aldehyde and ketone, and then again up to this, and then we will go through some features, explain why type question. After that, I will close the UV spectroscopy and go to the next reaction mechanism. So probably next practical class, Wednesday, I will complete this one and then go to the reaction mechanism on Thursday. Okay. So that is the difference. Now this one, you will go through this one. It's very interesting. Maybe you will be enjoying, because you are in a free mind, so you will be enjoying. There is a present. Okay, so I can leave now. So that okay, bye.
Okay, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.